All right, you guys, so this is our week 6 wrap-up video. And so this week we were looking at like molarity and solutions, and we just started acids and bases on this week 6. So let's see, most of your questions revolved around the 3 problems I'll present today. And so the first one was this one. You have an aqueous solution that is 1.00 molar sodium chloride. How would you use it to prepare 75.0 milliliters of a 0.350 molar sodium chloride solution? And so whenever you have this kind of problem where you either want to dilute something or you're trying to figure out, how much of a stock you need, you're always going to go to this equation that was presented in the top hat content. So it was presented as C1V1 equals C2V2. Sometimes you might see this equation as M1V1 equals M2V2. Remember, the C is for concentration, the V is for volume. In this case, your concentration is given in molarity. So remember, capital M is molarity. That's a way to give concentrations of solutions. It's moles over liters. And then again, V is volume. And again, sometimes these subscripts, here it's 1 on the left side and 2 on the right side of the equal sign. Sometimes you might see initial on the left side and final on the right side of the equal sign. Any of that is fine. So there's always kind of 2 things that I see students struggle with when using these equations. One is to make sure you are plugging into the equation correctly. So when you're taking these values and plugging them in correctly, my advice there is just to keep them together. What does that mean? It means you want 75 mils that is 0.35 molar. So keep that 0.35 molar. Remember, that's a molarity and a concentration. So you're going to plug that in for C or M, doesn't matter. And it goes with the 75 mils. Even if you mess up what side of the equation to put on, as long as you keep them together, you'll get the right answer. And so the question's asking you how much of this 1 molar solution you need. So it's asking me for the volume of that 1 molar solution, which should be in like milliliters or liters. So this concentration is out by itself. So again, just making sure you plug it in. Oh, we'll look at that in a minute. And then the other thing I see students struggle with is knowing what the answer means. It's like you get this answer, but you don't really know what it means. So let's take a look. So I set up the problem down here. And you can see I kept the 0.350 molar together with the 75 milliliters. And another thing with this, as long as you're consistent with your units on both sides, like this is in molarity, this is in molarity. If this is in milliliters, then your answer will be in milliliters. As long as you're consistent with your units on both sides, you'll be fine. This is one place, you could do liters, you could do milliliters. It's just remember, whatever you do on one side, you have to do on the other. Okay. So again, I put in 1 molar for our first concentration. We're looking for how much of that 1 molar solution we need. And then we want to end up with our final concentration should be 75 mils, the volume, so how much, and it should be 0.350 molar, okay? So when I carry out this calculation, it's 0.350 times 75.0 divided by 1. I get my volume is 26.25 milliliters. So now that second point comes in is, what does that answer even mean? Okay. So it just means that you need 26.25. In this case, we only had 3 sig figs, so I had to round up to 26.3. So we need 26.3 milliliters of that 1.00 molar sodium chloride solution. We would put that like in our beaker or in our flask. And then we would add water. So we would be using a graduated cylinder. Okay, we would add water to get up to 75.0 mils. And once we did that, we would have 75 mils, and we know its concentration would be 0.350 molar. Okay. So again, 2 things is just making sure you're plugging in correctly and then knowing what that answer means. Like if you're in a lab working, what do you do with this 26.25? And what you do is down here. Again, 26.3 mils comes from the 1 molar sodium chloride solution, and then you would dilute it by adding water to get up to 75. Okay. Oh, this is kind of a funny question, but which solution's boiling point deviates more from that of pure water? And it was a 1 molar solution of calcium chloride or a 1 molar solution of this sodium nitride. And in that lesson, there was a sentence that said, for every mole of particles dissolved in a liter of water, the boiling point of water increases by about 0.5 degrees Celsius. Okay, so for every mole, we increase the boiling point. And that's, again, that's in 1 liter. Okay, so the point is, the more moles you have, the more you're going to increase the boiling point of water. So if we look at calcium chloride, from its subscripts, from its chemical formula, okay, there's 1 calcium, there's 1 mole of calcium, and again, there's a 2 here, so there's 2 chlorines, there's 2 moles of chlorines, okay, for every mole of calcium chloride. For the sodium nitride, right, there's 1 mole of sodium and 3 moles of nitrogen for every mole of this sodium nitride. And they're both equal, they're both at 1 molar, so they have equal concentrations. So the fact that the sodium nitride has 4 moles of atoms, right, rather than the 3 moles of the calcium chloride, so the sodium nitride is going to cause that boiling point to increase farther away from the boiling point of pure water than the calcium chloride, because again, the calcium chloride only has 3 moles of atoms. Okay, so it's pretty straightforward, and it's just, again, which compound has more atoms making up that compound. Okay, now this is on acids and bases, and I know a lot of you were confused. The following week we did a lot more with acids and bases, so I hope some things did get cleared up, but again, I will talk about it briefly here. So an acid is defined, we have these 2 ways of defining it. This top one is the Arrhenius definition, and the bottom one's the Bronsted-Lowry definition. So this just, I kind of use whichever definition works best for me at the time. Oops, sorry. And I find myself using the Bronsted-Lowry definition the most. But okay, let's look at this. The top one, the Arrhenius definition. It's a compound, any compound that increases the concentration of hydrogen ion. And again, remember, that's also known as a hydronium ion. It can be represented by H plus or H3O plus hydronium in an aqueous solution. So if we look at our example down here, HCl, we know is an acid. When it's in an aqueous solution, meaning it's with water, it will donate its proton to the water molecule. That leaves behind chloride, so we get this Cl minus, and the water accepts that hydrogen atom, or hydrogen ion, I should say, sorry, and forms this H3O plus. So that's showing you, again, this compound HCl is increasing this H3O plus when it is in an aqueous solution, meaning with water. So that's our first definition. Bronsted and Lowry is a compound that supplies a hydrogen ion in a reaction. So with Bronsted and Lowry, it's saying like it's a compound that like gives up protons, gives up H. And again, remember that H plus, that hydrogen ion, a proton, is equivalent to this H3O plus. So we can also see that in this figure. HCl is giving up its proton, and then it forms that H3O plus. So both definitions are depicted in this one illustration, and we'll talk more about this in a minute. Okay, so on the opposite end of that was a base. So again, for the Arrhenius definition of a base, it's a compound that increases the concentration of hydroxide ion, so this OH minus in an aqueous solution. So down here we have ammonia acting as a base. We can see it's accepting a hydrogen from water. And when we do that, we have this OH minus, this hydroxide ion left behind. And we end up with NH4 plus and OH minus. So we are producing this hydroxide ion in an aqueous solution, and therefore that's kind of meeting the requirements of the Arrhenius definition of the base. Bronsted-Lowry says that a base is a compound that accepts a hydrogen ion. Remember, the acids give up hydrogens. Well, bases with Bronsted Lowry accept hydrogens. And so we can see that as well. The ammonia, the NH3, is accepting this hydrogen from the water, and it's becoming NH4 plus. So again, both definitions are depicted in this one illustration. Okay, but that wasn't really the question brought up on the discussion board, but I just thought I'd go over that. This was the question that some people had expressed some confusion on. And is a strong acid is defined as, okay? And basically it just means a strong acid is simply an acid that completely dissociates, okay? So notice here, this one-way arrow pointing to the right. So HCl, hydrochloric acid, is one of our strong acids. Every molecule of HCl, when it goes in water, gives up a proton, every one of them. It gives up the proton to H2O, forming chloride ion and H3O plus, the hydronium ion. And that's depicted on the left here, okay? So you can see in red represents kind of the acid, the white represents the proton, the hydrogen, okay? And if they're separated, we got that proton, that H3O plus, that H plus, and then the negative ion, so that could be chloride ion. So you can see here, that's adding the strong acid, all the white and red circles are together, but then once it hits the water, they're all split up. They've completely dissociated. They've completely ionized, okay? They form their ions, chloride and this H3O plus, and so they ionized and they dissociated. They no longer are associated with each other. Okay, so that's a strong acid. Now let's compare it to a weak acid. Here we have acetic acid, okay? And so we have our acetic acid with water. Notice there's a double-headed arrow here, okay? Because a weak acid only partially dissociates. It only partially ionizes. Pick which word. So some of the acetic acid molecules will give up a hydrogen to H2O and form this acetate ion and the H3O plus, but some are going to hang on to it. Some are going to still hang on to that H plus, and that's what makes it a weak acid. So again, if we look at the right side of this illustration, we'll see in red here are the acetate ions associated with that one proton. And before they hit the water, they're all together. They hit the water, and some of them are still together. And some of them are dissociated. Like here's one that's dissociated, okay? The acetate separated from the proton, the H plus. And so that's a weak acid. Some stick together, some don't. Strong acids, they completely always dissociate, okay? So that's, again, a strong acid versus a weak acid. And the same ideas go with a base, okay? Happy studying, guys.